Hello everyone, in this video we're going to be talking about how to make alcohols through reduction. So we're going to be getting alcohols from aldehydes, ketones, acid halides, and the esters. So typically I'm going to be talking about two main type of reducing agents, and the third one is going to be the hydrogen in the presence of catalysts. So let's focus on the first two, and one of them is NaBH4. And before I do anything in terms of reactions, I want to talk about the NaBH4, and I want to talk about the LiAlH4. So NaBH4 with sodium borohydride is actually a mild reducing agent, and since it's a mild reducing agent, it can be used in the presence of solvents such as water and ethanol or even methanol. However, when it comes to lithium aluminum hydride, this is a strong reducing agent, and since it's a strong reducing agent, it's going to be used only with ether as a solvent, and you can also use THF, as THF is just an ether but a cyclic ether. Now, why there isn't a difference between the NaBH4 being a mild and the LiAlH4 being a strong reducing agent, it has to do with electronegativity. So if you look at the boron versus aluminum, boron is going to be more electronegative than the aluminum. So as a result, the aluminum hydrogen bond is more polar, and it's more reactive in a sense, and it could also act as a base in that particular case, and that's why you want to make sure you don't really use any solvent that has protic hydrogen in there, such as methanol and water. Otherwise, it will just do an acid-base reaction instead, but you don't really have to worry about in the case of NaBH4. Let's come down to the H2. So H2 has, we will see mixed answers in the books. Uh, so if I ask you a simple question, does H2 reduce aldehydes, ketones, esters? The answer is going to be yes, but under what conditions? It's not going to be as simple as reducing alkenes and alkynes when you're using this hydrogen in the presence of a catalyst. In case of alkenes and alkynes, you can use mild temperature, mild pressure, but when it comes to these aldehydes, ketones, and esters, you will need really harsh conditions to perform the reduction. So we're talking about very high temperature and very high pressure, and how high the pressure and how high the temperature going to be, that depends on what particular function group you're really talking about. So it does work, but sometimes it's not that practical because you have to have really high temperature, high pressure. And if you can just go ahead and get those work done with NaBH4 and LiAlH4, so why not just use that instead of using the H2? So since the NaBH4 and the LiAlH4, they are uh, the mild and the strong reducing agents. When it comes to aldehydes and ketones, you can use any one of those. So that's why I have both of those in there. So I can, if I want to go ahead and use NaBH4, so I'll go ahead and use NaBH4, and I can do that in the presence of methanol. And typically, this is going to be worked up with the acid, a dilute acid at the end of the day. And sometimes you may not see the acid, dilute acid, or maybe just water is okay as well. So if it's in a secondary, if it's in a ketone, then you will end up making a secondary alcohol. Now, this stuff, I'm not going to talk about the mechanism here. I'll have a different slide where I'll talk about the mechanism. But this, right now, this carbon is an sp2. So it's a planar structure. So when we get the hydride from the NaBH4, it can do either a top attack or a bottom attack. So as a result, that means your OH that's going to be on this particular hydrogen, on this particular carbon, it could be out of the page or it could be back into the page. So I'll have a shot of making a pair of enantiomers there. Well, let's look at this next one. Now, this next one is an aldehyde. So aldehydes, whenever they get reduced, they make primary alcohol. So if you have a ketone, that get reduced to secondary alcohol, and they could very well be racemic mixtures if that center is chiral. But but the aldehydes will go ahead and make only the primary alcohols. So this is how it's going to look like. And this is not a chiral center, so I don't really have to worry about the stereochemistry there. And I can use either one of those reducing agents, whether the NaBH4 and LiAlH4. And keep in mind the H2 will also work, but you have to have really harsh conditions. So I'm not really going to put that out here. Uh, so if I want to go ahead and use the LiAlH4, so that would have been in the presence, THF can be used as a solvent, and then you can work it up with the acid. What about the next one? Now, this one is going to be the benzene along with, you have a ketone there, and I can go ahead and use something like LiAlH4 with THF, and then I can work it up with dilute acid, or even water would be fine in here. And remember, this is a ketone and it is in a chiral center, so I would get a pair of enantiomers there, because I can have the hydride either doing the top attack or doing the bottom attack. So as a result, you can have the OH either out of the page, and if the OH is out of the page, that means your hydrogen is going to be going back into the page. I just didn't draw that in the previous case, but you don't really have to draw the hydrogens, and obviously you can have the enantiomer as well. If I'm using any one of those, whether it's a LiAH, LiLH4, or even NaBH4, they're not going to be able to reduce the double bond between the carbons, because the double bond between the carbon is not polar, and this hydride works on the works on the principle of polarity. Carbonyl is the polar, where you have partial positive here and partial negative here, and as a result, this hydride, either from NaBH4 or from LiAlH4, can do the nucleophilic attack at that particular carbon of carbonyl. But it can't really do that in case of the double bond between the carbons, because it's not polar. So this one, I can just copy that down here, and it will only reduce the carbonyl, and as a result, I'm going to get, again, this is a chiral center, so I can have the OH either coming out of the page or going back to the page. So I'll make a pair of enantiomers, and you will have the same result even if you use LiAlH4. Okay, you can also use the either NaBH4 or also the LiAlH4 in case of acid halides. So X here is going to be the chlorine and bromine. Those are the most common one. And these acid halides are also very reactive toward the nucleophilic attack. They are more reactive than the ketones and aldehydes. So as a result, you can use a mild reducing agent such as NaBH4. So if you can do anything with an NaBH4, you can do the same stuff with LiAlH4, because that's even a stronger reducing agent. And then you can just work it up with the acid. The only thing here is you're going to be needing at least 2 equivalent of NaBH4 or excess. And the reason why, you'd have a good leaving group, so it does make an aldehyde at the end of the day. So this is going to be a primary. Um, this does make an alcohol at the end of the day, and it's going to make a primary alcohol, but it actually goes through the formation of an aldehyde. So because you have a good leaving group there, and upon the nucleophilic attack by hydride on the carbonyl, and when that tetrahedral intermediate goes back to create the carbonyl, um, carbonyl functional group there, the X would leave in that case, and you will end up getting an aldehyde in the beginning, and in the next step you will make the you will make the alcohol. So this does require an excess NaBH4, at least 2 equivalent of NaBH4, and the same can be said about the LiAlH4. So if you're using acid halides, then you want to use excess LiAlH4. So it does make the aldehyde, and then eventually gets to the alcohols. Now let's talk about when, under what conditions we're going to be using the LiAlH4. So this is a strong reducing agent, so we're going to be looking at esters and acids, especially, and even amides and even nitriles. We're not going to be talking about amides and nitriles here because they don't really make alcohols upon reduction, but they make rather amine. But I'm just going to be focusing on esters and acids. So now these guys are not as reactive toward the nucleophilic attack. As a result, you will need a stronger reducing agent. So keep in mind the NaBH4 will not work in case of esters, acids, amides, and the nitriles. You will have to have LiAlH4. Now the question is, will H2 work and the catalyst like we have said earlier? And if I want to say the simple answer, and the simple answer is going to be yes, but under wet conditions, we're going to be needing a really high pressure and really high temperature. So that has to be very specific of how high the temperature and pressure needs to be in case of the reduction of esters and these acids and amides that can be done under hydrogen with catalytic in the presence of catalyst. The only one that actually really works, so if I just kind of go back here, the only one that will really do reduce any of the carbonyls under mild conditions of H2 with a catalyst. So we still need some high temperature and pressure, but not that high, relatively mild conditions. So you could have palladium or even nickel. You could convert this acid chloride into an aldehyde. So whether or acid halide, you can have chloride or the bromide, but it will stop right there. And this particular one is called Rosenmund reduction. But if you want to go ahead and convert it from the aldehyde to the primary alcohols in the presence of H2 and the catalyst, you will need a high pressure and high temperature, but this could be done under relatively mild conditions. Let's go down here. So if you have this acid, I'm going to be needing an excess. In the first step, I'm going to be using an excess of LiAlH4. And one of the reasons why you need an excess of LiAlH4 is the first step would be an acid-base reaction, because remember this acid has an acidic proton, and this LiAlH4 can also act as a base. On the other hand, the NaBH4 doesn't really act as a base, and that has to do with the electronegativity difference between the aluminum and the boron. And obviously, you want to work it up at the end of the day with dilute acid or just even with water, and it will go ahead and make a primary alcohol. So just kind of keep in mind how many carbons I need. So 1, 2, 3 carbons there in the main chain, and you end up getting a primary alcohol in this case. The same result will take place when you're using the ester, like in this case. So I want to go ahead and use LiAlH4 in the presence of as an ether as a solvent, and you can work it up with dilute acid. Um, so again, it's going to make primary alcohol, and it does go through the formation of aldehyde, but then eventually the aldehyde gets converted into an alcohol. So remember, they're actually going to have two products because since it's an ester, so this is going to be one side that's going to make an propanol, but then you also have, if I change the color here, you also have this stuff right there that's going to make a second type of alcohol there. So if you have multiple organic products, you got to write all of them. So the bottom line is when you're trying to reduce either aldehydes, ketones, or acid halides, you can get away with NaBH4, or you can also use LiAlH4. But when it comes down to reducing something like acids, esters, amides, and nitriles, you got to use a strong reducing agent. The LiAlH4 will work in that case, and the NaBH4 is not really going to work in that particular case. Let's look at this example before we go. So I got multiple things going on here. I got a ketone group there. I got a double bond between the carbons, and I got this particular ester group as well. So suppose if I go ahead and use, in the first step, if I use NaBH4 in the as a methanol as a solvent, and I can work it up with dilute acid at the end of the day. So since this is a mild reducing agent, it's only going to reduce, so I'm just going to copy this thing down actually, just for the sake of time. So it's only going to reduce the ketone. It's not going to reduce the ester. It's not going to reduce the carbon-carbon double bond. So the only thing I'm going to really have here is this guy here. And obviously this could be into the page or out of the page, so I can make a pair of enantiomers there. Now, if I use, suppose, LiAlH4 and THF can be used here, and then the secondary would be your acid workup. Now, this is actually capable of reducing both the aldehydes and also the ketones and the esters. So another way of saying I can reduce both this carbonyl and also the ester carbonyl. So at the end of the day, we'll end up getting, just copy this down here. Now this carbon that's at the ester position is not really chiral. It's going to end up making a primary alcohol. So I'm just going to go ahead and write down an OH there. And this particular one, the ketone one could, the OH could be into the page and out of the page, so I can have an enantiomer. And also keep in mind the other product you will possibly have here is the ethanol. That's going to be your organic products. So again, we didn't really reduce the carbon-carbon double bond because it's not polar. So now if I actually want to go ahead and use, suppose, just the H2 and maybe palladium or just a nickel, but relatively normal conditions, not too harsh conditions, then it's not really going to reduce all of them, but rather it's only going to reduce the carbon-carbon double bond. So that's the thing you want to keep in mind. The only carbonyl that can be reduced under normal conditions, that would be your acid halides. But obviously we don't really have the acid halide here, so we only reduce this carbon-carbon double bond in the presence of H2PD relatively normal conditions. So when we say a normal condition, maybe few atmosphere pressures and maybe 56 degrees Celsius temperature. But now suppose if I run the same reaction under harsh conditions. So when we say harsh conditions, I'm talking about very high temperature and very high pressure. So I'll say high temperature and high pressure. So we're talking about maybe 300 degrees Celsius or even more, or we're talking about a couple of thousand psi here. Now, under this condition, it will be able to reduce every single thing we have in this particular case, whether it's in a ketone, an ester, or a double bond. So I'm going to go ahead and take this out. Just keep track of your carbons there. So this is again going to be a chiral, so you can have the OH in and out of the page. This last one is not going to be chiral, so I can just draw that OH as in a primary alcohol there. And obviously you can have the enantiomer there, and the other products would possibly have here would be the ethanol that's going to be coming from the ester group. All right, so this is what we're going to be looking at in terms of reduction, how you're going to be making alcohols using reductions of aldehydes, ketones, acid halides, and esters. If you have any questions, feel free to leave any comments in the section below.